So again, we're interested in finding the area between the graphs of two different functions, or we're trying to find the area between two different curves. So here is a picture of this. It's slightly different from the picture that I graphed on Desmos. The red function f of x is on top, and the blue function g of x is on the bottom. But we're still interested in the amount of area bounded between those two different graphs. When I was looking at this with the sine and cosine functions, it made enough sense to start and to stop my integral at the two different x coordinates where those graphs met. But that's not a strict requirement. We can start and stop our integrals wherever we please, just so long as those functions are defined and have antiderivatives the whole way through. So I can imagine starting at some x coordinate a on the left and ending at some x coordinate b on the right. Now, if I want to do everything formally, I'm going to set this problem up in the same way that we would have used Riemann sums back in Calculus 1. So the idea is I can't directly compute the area, but I'm going to fill it up, fill that area up with rectangles. We pick rectangles because rectangles have a very nice area formula, base times height. Now, the base of each of these rectangles is going to be a section of the x-axis, and I'll call that delta x for change in x. If it's been a while, that's okay. I like to think of it, whenever I'm doing Riemann sum kinds of things, that I use Greek letters for the macro level operations, the big chunky bits. So my delta x here is a section of the x-axis, an interval. The delta x here is just telling me how wide my rectangle is. And I'd like it to be the same width for every single one of the rectangles I'm using to fill that area. I also need to have a height associated to each rectangle. And here I have some more flexibility. Different rectangles can have different heights. You can see that in the picture. The height of each rectangle is going to be the distance between the curve f of x and the curve g of x. So the trick is, at each different rectangle, maybe we'll have the first rectangle, the second rectangle. Abstractly, I can say, what is the height at the ith rectangle? Well, I'm going to pick some coordinate xi star, and I'm going to use that xi star coordinate, my sampled value, in order to just calculate both functions at the very same x coordinate. Whatever the difference of those functions is, will now be the height of my rectangle. This should all seem familiar, just that back in Calculus 1, our g of x was always 0. We were always stopping at the x-axis. Now that we're learning more advanced integration techniques, we don't have to do that anymore. So we can choose what kind of sampling we want to do. No matter which version of sampling that we choose, there is going to be some approximation error. So we can do left-hand endpoints, we can do right-hand endpoints, we can do midpoints. Those are all fine ways to work on Riemann sums. But whatever we choose, The approximated area is this Riemann sum formula. So supposing there are n different rectangles, I need to add up n pieces of area. Each of them has the very same width, delta x, and the height of different rectangles is going to be modeled by f of xi star minus g of xi star. And again, as we take more and more rectangles, the error gets less and less. So I'm going to take a limit. The value of this limit will give us the area, the actual area between the two different curves. And again, I have reserved Greek letters for my macro level stuff, where I'm using a finite number of slices and whole intervals to model the width of my rectangles. After I take the limit, I revert to the Latin alphabet. So my capital sigma becomes my stretched out s to make the integral sign, and my deltas become a dx to represent that I'm taking pieces of the x-axis. But the formula that I get, my area formula is, gosh, f of x minus g of x dx, integrate from a to b. Why, that is exactly the answer that my intuition said to use.